Hello class, this is Mrs. Ayodeji with today's video on chapters and sections 14.2 and 3, implicitly defined curves, circles, and ellipses. As you're watching the video, please write down important information, vocabularies, formulas, and equations. Feel free to pause, rewind, and repeat the video as often as you need to get a clear understanding of what is occurring in the video. And at the conclusion of watching the video, write a brief summary about what occurred in the video and submit that summary as well as a top comment on at the end before class starts. All right, let's begin. So we're talking about implicitly defined curves first. And so first let's talk about explicitly defined curves or functions, because that's what we're used to experiencing. And this is an example of y is equal to a function of x. And this is called an explicitly defined curve because y is an explicit function of x. In other words, it means that it's obvious that y depends on x, and that's why we call this an explicitly defined function. And when graphed, explicitly defined curve. Last video we talked about parametrically defined curves, and they look like somewhat like a piecewise function. But each of the pieces are dependent on t, so we call that a parametrically defined curve. And we're looking at an example of this in another format. And today we're going to learn about implicitly defined curves, which we've seen before, but we've never called them implicitly defined curves. In this case, this is an example: x squared plus y squared is equal to 1. And so the dependence of y on x, or the dependence of x on y, is not as obvious as it is in this case. So even though we can write these expressions in terms y in terms of x, as this is an explicitly defined function because it's obvious that y is dependent on x, but this is an implicitly defined function because it's not that obvious. We have to do some manipulations in order to get that to be the case. Okay, so that's just the new vocabulary word, implicitly defined functions. Here's an example of an implicitly defined function because it's not obvious that y depends on x. So this is implicit, whereas the ones above, it is obvious because it says y equals some function of x. Okay, so the rest of this unit is going to talk about conic sections. And if I were to take a cone and intersect a cone with a plane, I'm going to get a variety of shapes based off how I intersect that cone with that plane. So as you can see here, this intersection of this cone with this plane creates a circle. If I intersect this cone with this plane, it creates a parabola. If I intersect the cone with this plane in this manner, I get an ellipse. And if I intersect it in this manner, I get a hyperbola. So all of these are not necessarily functions, but they are curves that appear on a two-dimensional grid. And that's based off of how the plane intersects the three-dimensional cone. So we're going to focus right now on circles, and you're very familiar with it. And since the last unit was about parametric defined function equations, we're going to look at the parametric equation of a circle since we're familiar with it from the previous GEA in class. And in this case, this represents a circle with center HK. So here's my H and here's my K, and the circle has a radius R, and that's the component of it. And we define it because it's parametric. We define a domain for t, and we usually define it between 0 and 2 pi because that's what it takes for the parametric equation to complete one full revolution. So let's look at an example in decimals. So here's my origin, and the center of a circle I want is going to have x and y coordinates that we usually label as h and k. So if I want to change the location of the center, I change the values of h and k in order to get a different center. And if I want the radius of my circle to be 1, then I can express that circle using this implicit form. Implicit form is x minus h squared plus y minus k squared, which I'll talk about in greater detail later. But I can also represent it with the parametric form as we see right here. And if we were to move t as t goes from 0 to 2 pi, you see it takes one complete revolution of t to make the circle as well. So that draws it out. And if I change the radius and change the location of the center, I still will create the same shape with the center based at the h and the k, and the radius being, in this case, 3. So one thing I help to remind myself on how to write the parametric representation of a circle is that x is related to cosine and y is related to sine, okay? Which makes sense because from trigonometry we know that the point on a circle can be related by r cosine theta, comma, r sine theta. Okay, so then earlier I showed you the implicitly defined formula of a circle, and I want to show you why it works. So if I take x minus h is equal to r cosine t, so I got r cosine t by itself, and I get r sine t by itself. Then that means when I square both sides, I'm going to get this expression, x minus h squared is equal to r squared cosine squared t, and y minus k squared is equal to r squared sine squared t. And if I add these two together, I get that x minus h squared plus y minus k squared is equal to r squared cosine squared t plus r squared sine squared t. Factor out the r squared, we get cosine squared t plus sine squared t is equal to 1, which is equal to r squared. And so that's why we have an implicit equation for the circle that looks exactly like this, where again h and k represent the center of the circle and r represents the radius of the circle. Okay. This is called the standard form of the equation of a circle, or general form is sufficient. So in summary, we're talking about different ways to express a curve, and we started with the parametric equation. Then we looked at implicit forms. In this case, this is the standard or general form that we talked about up here. But I can also rewrite it by expanding out each of these factors, and it looks something like this, or looks something like this by combining like terms. And they all represent implicit forms of the exact same circle. So if I want to describe a curve defined by this particular equation, my suggestion is to get this into the form where x squared and y squared are on the same side of the equation. And a constant is outside the equation on the other side. And then completing the square, complete the square. In this case, we added half of 10 divided by 2, half of 10, which is 5, and squared it. And we added and subtracted 25, added and subtracted 4. And we end up with this expression. Move the 29 to the right side, we get this expression, which is in the general standard form of a circle. So this tells me that we have a circle with radius not 9, but with radius 3, centered at -5 and +2. All right, last thing we're going to talk about is section 14.3, which is ellipses. And you guys may experience ellipses before in elementary school, and they consider them to be squash circles. And so we're going to start with the parametric form of the ellipse, and it looks very similar to the parametric form of the equation of a circle. The only difference is that there is no radius because it's an ellipse. A and B are in place of the radius in the parametric form of a circle, and that's because in a circle A and B are equal to the same number, which we call the radius. But in ellipse, A and B can be different. And we usually have A and B being positive. And we're going to see in the GEA that in an ellipse, the ellipse has a horizontal axis with length 2 times A and a vertical axis with length 2 times B. And the major axis is usually the longer axis. So it could be the horizontal axis or vertical axis, depending on if A or B is bigger. So in this case, we're going to graph this ellipse. And it looks very similar to the parametric form of a circle, but as you can see, these values are different, so that lets you know we have a pure ellipse. And since this value 5 is bigger than 2, that means our horizontal axis is a major axis and it has a length of 10 units, and the minor axis is the vertical axis and it has a length of 4. So the center of the circle is 7, 4, and this is the major axis, 10, the length is 10, and this is the minor axis, the length is 4. So here we have a lovely center at 0, 0. Our HK is at 0, 0. I'm not going to change that. And then this is our parametric expression of an ellipse. And so as t goes from 0 to 2 pi, it makes this type of path, which, as you can see, is in the shape of a circle. And this is the implicit description of ellipse. In this case, I changed A so that A is smaller than B, and as you can see, we have a longer ellipse. And if I want to make a lengthwise ellipse, I have to make A longer than B as well. And then the length of that major and minor axes will change. Okay, let's take a look at something else. So let's look at how you can implicitly define an ellipse. So if you remember, x equals h plus a cosine t for the parametric definition of an ellipse. If I subtract h from both sides and divide by a, we have cosine t is x minus h over a. And then if I do the same thing for y, I get y minus k over b is equal to sine t. So if I square both sides and add them, so square, square, and add them, then I get something that looks like this. And we know that cosine squared plus sine squared is equal to 1. So the general form of ellipse for the implicit form looks like this. Okay? And that's the conclusion of our video.